Thanks a lot. I'm very honored to be here. And I make a bet that I'm the only person in recent memory who came here to give a talk without asking for funding after that. No? Okay, so I'm not going to be asking for funding for some kind of moral reason. That I effectively think that if you can be independent as a scholar, you should stay independent. Anyway, so my background, I was an option trader for 21 years. And I retired into becoming a academic. And in fact, it's the reverse. I was retired as an option trader, and academics have to work for a living. And so this is what I'm doing now, working for a living. So it's an inverse retirement. So I'm going to be talking about a lot of things, try to link them together. My last book is called Antifragile, and we're going to see why it's called Antifragile. It's a very strange title. But it concerns things that gain from disorder, things that gain from randomness, from a bunch of things. Let me first start with a statistical problem that sort of motivated me in my previous career as a trader. My specialty is tail events, rare events, events that don't happen often, but when they happen, in some domains they have massive consequences. You take, for example, the stock market. You have 12,000 companies listed, maybe 100,000 that came to the market, all right? So the base population is very large. Out of all these companies, maybe about between 50 and 350 will represent half the capitalization. Okay, it's not very good. With drugs, I think it's same thing, same story. It's a power law tale where typically it's not the 1%, 99%. Typically it's 0.01% will represent the bulk of the properties. In finance, things are worse because of convexity effects that I will discuss that sometimes make one day in the life of a trader represent 95% of his entire lifetime variations one day because of convexity effects. So let me, I'm showing you a graph here for those of you who are into statistics. Most of what we work with is called the Gaussian distribution. And there is a measure of how much things depart from the Gaussian distribution in terms of how much of the deviation can be explained by a small number of events. You agree? Okay, what's the name of the measure? The Lee kurtosis. It's so common, it's on Excel spreadsheet. So when I tell people the data has fat tails, they say, well, yeah, but we know that. We don't know that. The problem is people have accepted that the data has fat tails without taking it to the logical conclusion. How fat are the tails? Okay. How much do we depart from a Gaussian? Well, you're going to be in for a surprise. When I wrote the Black Swan is about these events that are outside the realm of expectation in some domains representing about everything. Okay, about everything. In the computer business, for example, one company, Microsoft, you had 50,000 software companies, and they had the bulk of the revenues. Okay, so the exception is almost everything. Same in literature. 1 million novels on the market, small number of authors are published in literary, I'm talking about literary fiction, all right? That certainly would include a lot of things like, say, Armstrong's, it's not literary though, Armstrong's memoirs, but that's not literary, the cyclist. But we definitely, but in that domain called fiction, you have, so out of the million, you have about a small number published. Of these published, about maybe 5 books, maybe 35 books will represent half the sales and a bulk of the profits. So the exception is everything in some domains. That was my idea of the Black Swan. And then when I wrote it, of course, the people tell me, of course we know that. If you know that, you can be in that business, my typical answer. And I had on the web a lot of data setting that nobody was paying attention to. I took every single piece of economic data you can find that you could steal, find, buy, the kind of thing, all right? So put them on a computer. It's about 20 million pieces of macro variables, we call them. Changes in gold prices, silver, coconut oil, lumber, freshly cut lumber, all these commodities, and of course single stocks. So about 20 million pieces of data of each. One for non-stocks, one because a lot of stocks, all the variations. Put them on a computer. and try to figure out, you remember that notion of kurtosis tells you how much the things are fat-tailed. Try to figure out how fat-tailed the data was. When you take 40 years of data, what you have here is how much of the total kurtosis is explained by a single day, one day. In the US stock market, one day, October 1987, I had hair then. I was a trader. Okay, I had a lot of hair. Not a lot of hair, but say, okay, it was not the same. And effectively, that's the event that marked my life. And at the end of that day, I decided to be a specialist on one thing, fat tails, rare events. So that day represents 80% of the kurtosis of the last 40 years, 10,000 observations. Now, of course, silver has some variation, 99% in one day. I also was there. The other one was not necessarily there. But if one observation represents so much of the kurtosis, it means you cannot use, you don't know how fat the tails are, or you can't use, more technically, the norm L2. You can't use it. In other words, anything, in practical terms, anytime you hear for socioeconomic data that are fat-tailed, the word regression analysis, standard deviation, correlation, anytime you hear this, close your ears. And take the paper, take it, and dump it in the garbage because it's inconclusive. Except for data that are bounded. If you have bounded data, then it works. Otherwise, just put it in the garbage. Okay? And that was my war with, I said, econometrics. Professor Engel, I said, anything, it works beautifully on a computer and for the Nobel Committee. But unfortunately, in the real world, it doesn't work. When I tell you, sometimes you can have such a high portion of the kurtosis. Okay. The other thing about stress testing. Now, people tell me, okay, we're not using parametric analysis. We're going to use something called stress testing. All right? Now, stress testing, we look what happened in the past, take the largest deviation in the past, and we're going to use it as an indication of the next, what can happen in the future. You agree? Seemingly very rigorous. It's how banks operate, by the way, all right? By using stress testing. Now, the problem is, Mr. Greenspan went to Congress, and when he complained about the crisis, why he didn't see it coming, he said it never happened before. Not a single congressman had the presence of mind to tell him, but Mr. Greenspan, you never died before. Okay, all right? But effectively, to be a little more rigorous, when you make a statement, this never happened before, you should be able to prove that large deviation has to have a predecessor, you see? The same data, we take here large deviations. What I have in the vertical is up till period, I can't see it well, but say up till period T, up till 1980. You take all variations in one commodity up till 1980. All variations that are in the tails, say, you arbitrarily say worse than 10 standard deviation if it were Gaussian or 10% or whatever it is, and see what would happen on a horizontal axis in a year after, okay? If the past predicts the future for tail events, you should have something like that. And effectively, the regular deviation predict regular deviations. Like you see this cloud, okay? Rate deviation, this is what you see. Okay. In other words, large deviation don't have a predecessor. So saying it never happened before is no excuse. And actually, you don't even need data, you just need logic. The crash of 1987, the market went down 23% in a day. All right. The worst day before that was 10%. So if you're using that method, you wouldn't have seen the crash of 23%. But what do people do now? They calibrate the worst-case scenario to the crash of 1987. It's called lack of recursive thinking. All right, I had to write a chapter on it, wondering if there's some form of disease, mental disease called future blindness, not understanding. You have second-order thinking, or rather just plain first-order thinking. But it's very common in finance. There are other methods, of course, power law tails. And if you take power law tails, it's very simple. Say, okay, if God gave you the parameter, everything is nice. The problem is, look at the distribution on the left you have on a parameter. You calibrate power law tails for something, you get an alpha tail exponent. Without getting technical, there is a parameter, and that parameter is hard to find because it's not deterministic. It is, it has a distribution. So anyway, so this tells us that we can't really go very far. You're trying to predict future events. We don't even know the probability of large deviations. So let's get out of the prediction business. Let's try out of the business of trying to understand tail events in the future and save a lot of money. I testified in Congress against people who want to spend even more money, okay, to try to see future events. Those who didn't see the crisis coming think that, by putting more money, we're going to see more. Do Markov chain, things that typically are nice on paper, but the calibration is such that won't help you. So instead of all of this, let's try to focus on a complete different problem that we can approach with science much more rigorously, and it's called fragility and antifragility. Right? So let me now explain fragility and its opposite. When you have with the first thing about fragility is measurable, I was going to see, detectable, at least much more measurable than tail events. The probability of rare events is very hard, visibly. If you're trying to figure out the 100-year flood, we don't have, you need a lot more than 100 years data to talk about 100-year flood. In some places, 100-year flood plays a large role. So anyway, so let's forget about small probabilities for a minute and talk about, a different concept. When I ask people what's the opposite of fragile, typically they answer something like robust. Okay, nice word. Solid, adaptable, all kinds of spade of things. Well, it's not quite right, because the fragile, and we're going to see we can map exactly the fragile as something that does not like, if this were in porcelain, put here, it's fragile because it doesn't want volatility. It doesn't want variations, okay? It doesn't want peace and predictability. And we know a lot, as an option trader, we specialize in things that don't like volatility and things that like volatility, right? And the opposite of what doesn't like volatility is something that likes volatility. And that's not quite solid, okay? The Brooklyn Bridge doesn't care. It's not solid. It's solid. It doesn't care about volatility. So the opposite of something that doesn't like volatility would be something that would beg, the opposite of fragile, handled with care, would be something on which you would write, please mishandle, all right? So anti-fragile is a word I came up with. And of course, I keep getting, and now the rate is about 1 a day. It used to be 2, 3 a day. What difference with resilience? Incidentally, at Davos, they did the theme called creative resilience, or something like dynamic resilience, whatever it is. It's not really, resilient doesn't improve from shocks. You need something that benefits from shocks, something that has some attributes. And if I, for example, or benefits from disorder, if I buy 5 times the regular amount of the needed insurance on my house, okay, against earthquakes, burglaries, whatever you want, or the neighbor coming and trying to destroy my house, against everything, all right, 5 times, and I go on vacation, what do I wish for? Destructions, hurricanes, floods. Okay, so this is not adaptable, all right? This is a contractual thing. We have actually a name for it in trading called long gamma. Long gamma, something that benefits from disorder. And effectively, the Romans, I noticed, all these people had that concept that there's things that begin from disorder, things that thrive on disorder. When you remove disorder from the system, they hurt and damaged. So let me show you how we can map it mathematically and rigorously. This is in time series space. The first graph, forget the second graph because it will confuse you, and then we'll spend the night here. That's the second graph. So let's discuss the first, third, and fourth graph. All right. The first one in time series, variations are small, but down variations are large. It's a coffee cup on a table. Okay. Actually, I have a porcelain cup here. Coffee cup on a table. All right. Benefits are close to 0. All right. It either breaks or nothing can happen. So all the deviations are to the downside. You agree? Sort of like bank portfolios. All right. When someone comes to talk about the banks, you know it's not because they suddenly made a lot of money. All right. Okay, so it's sort of like, or you're on a plane and something happens, a large deviation happens, you know it definitely didn't improve. You know the plane crashed, all right? So this is sort of like number one, this is my mapping of fragile. Where deviations, the upper bound, just like I'm sending a package by mail, the upper bound is unchanged or unharmed or slight gain, and the lower bound is very harmed. Now, robust, the lower bound is unharmed, the upper bound is unharmed. It doesn't get better than unharmed, doesn't get worse than unharmed. It's very solid, all right? That's the third line. That's robust. And the fourth one is what you guys are in the business for here. I only discovered it now when it said National Science Foundation, your statistics, stuff like that. It took me 6 seconds seeing the email, replying without even finishing it, all right? I got here, and then at lunch I discovered in the car that you guys are in the business of funding projects. Well, you're in the business of this, the bottom right time series. This isn't time series space, where it costs you little. Sometimes you have small gains, but typically the big variation is the upside, no? Exactly opposite of fragile. So you're in the anti-fragile business. You're just, congratulations, all right? So this is. And then there's another thing, mathematically. For those of us who work in statistical matters, not outside philosophy departments, what likes volatility, variability, likes uncertainty, likes errors, because the errors, you have small downside from error, big upside. You see, if an error is symmetric in distribution, time, because time is for most distribution time series process, time scales at some exponent of sigma scales some exponent of time and vice versa. All right. So for a Gaussian, sigma squared root of time. So time and so this is sort of like what we. It sort of happens that what benefits from what we can characterize as fragile doesn't like these, and what's anti-fragile should like these. And of course, you're not anti-fragile against everything. Some source of randomness for up to a given intensity, as we're going to see. So, in probability space, which is my business, the first graph is robust. Why did I put robust first? Anyway, the robust has thin tails. No big probability of deviation, big either way, all right? There's a second graph here. It has thick tails on both sides. Believe me that the second distribution I almost never seen. Typically, the thick tails are only one side or the other. This is why I'm trying not to discuss it, okay? And we can discuss it, but it would be a waste of time. There's very little of it, all right? You observe very little of the second one, typically because you have an absorbent barrier. The thing is, something is fragile, even if it can have big upside, odds are it's going to break, ergodic, it's going to break. If it's breakable, it's going to break. So to be anti-fragile, you have to be non-fragile. You have to be robust on the left side of the distribution and open-ended on the right side. Now, the third graph is, of course, skewed left is fragile. Skewed right is anti-fragile in the probability space. With this, we can we'll do a lot of things. Now, detection. I wrote a paper, and the paper is available on the web. You can find it. It took me a long time bickering with referees, as usual, but it's a long paper where we define fragility, measurable as sensitivity of the left tail to changes in the scale of the distribution. Okay? That's exactly our definition of fragility. And everything flows from it. But we're going to see by theorem, the transfer theorem. This is more practically. S minus is the lower semi-deviation, is how that integral below k, this is k, the symbol is k, the integral below k thickens in response to an increase in, say, the scale of the distribution. To be more precise, we use S minus for the left side, the lower semi-deviation, mean absolute deviation below some number omega. This is a little technical, but to simplify, say you're working with a Gaussian or something that has a finite variance, you change the sigma a little bit and see how much that tail thickens. That's exactly our measure of fragility. Okay? That's what we call native fragility. Now, okay, this is technical, but if you're not in that business, I don't know who's interested in this. and maybe plus a little boring, or you can ask a question if you're more interested in this. But now we can work with detection of fragility through nonlinearities. There's something that bridges a function of a variable, the distribution of that function. We're going to see we can bridge, right? If if y is f of x, how y responds in reaction to changes in the volatility of x. It will make sense in a few minutes. But let me first explain fragility, map it, redefine it, and it's going to be the exact same definition in terms of convexity. For the fragile, you have to have some nonlinearity, necessarily in functional space. Let me explain. The fragile, say, when I jump, you see, if I jump 10 meters, I die. Even in DC, I don't know if DC, they die in DC, but typically outside of DC, people die, all right? I don't know, okay. You jump 10 meters, you die. Now, if you necessarily, because every meter, okay, hurts you more than the previous one. If you jump 1,000 times 10 centimeters, you're not going to die, you see. So there is an acceleration there. This is quite critical for us, okay, because this allows us to formulate, to understand that if you detect acceleration, if something depends on something else, I call it inherited fragility. My body in relation to shocks, all right? If you detect acceleration, then necessarily you will be fragile, okay, over some range. So the nonlinearity will map exactly, and we have a theorem showing exactly how it will map to thickening of the left tail. And we're going to see it in a few minutes. It's sort of some variation around Jensen inequality, not particularly complicated now that we found it, but nobody thought about it before, so maybe it's not complicated, but it's too uncomplicated for people to think about it. In the book, I have another story illustrating fragility with the story of the stone. There's a king. It's in Midrash Tehillim, in the ancient semi-Talmudic literature. There is a king who has a son he has to punish, and the punishment is to whack him with this big, huge stone, all right? But kings don't like to punish their sons, as you well know, right? And fathers don't like to punish their sons in general. So you have to find a way out of it, okay? So they probably had a member of the National Science Foundation around, who understands nonlinearities, who made the suggestion to the king, all right? I'm sure, I don't know who here, but someone who understands nonlinearity would go to the king with very simple problem. So how you break up the big stone in small pebbles, and then we order coffee, and then we pulp them a little bit, okay? So really, what you have here is acceleration. You see the linear exposure. This is harm, event size. You have to have acceleration. The size of stone, look at event size of stone up here, and this is harm, okay? You have to have acceleration of harm. If a lot of pebbles don't hurt you as much as a big stone. Actually, small pebbles leaves you intact, no? So you have to have acceleration of harm. Now, I use that for finance to detect risk in portfolios by saying if exposure is going to harm you, look at the linear. Here I have a zoom of this first portion for small variation. For small variation, the linear has shows a lot more harm than the nonlinear. But for large variation, the nonlinear exceeds the linear. Okay? All right. Now, this is my argument. This, I spent 5-6 years working on this. So by the time I was meditating for it to come out, 26 years, but I applied it everything, but didn't think of formalizing it, okay? Let me give you the other argument of why harm has to be in a nonlinear, okay? Think about the probability distribution. If your probability distribution has one mode of harm, not one mode of harm, you have a lot more regular than irregular. You agree? So things that have to survived have to be, all right, sort of not exposed to the linear. You see, let me rephrase it. Take earthquakes. Every day you have how many? About 4 million earthquakes? Okay, if it were linear, it would be a lot of damage. Given that we're here, conditional, having survived, you have to be nonlinear to earthquakes, all right? Or you take the Scoffy cup, given that Scoffy cup still exists, it has to be nonlinear to shocks. Okay, that's sort of like the conditionality argument. And then you can get that from the shape of probability distribution of survival probability maps automatically to convexity of harm, as it puts an upper bound on it, which makes it concave. This concave. Concave means harm because it's a negative of convex. Please, if you have a question here, ask me because that's the time to ask. All right. So, but the interesting thing in finance, look at here at the bottom. All right. I had that idea by telling everyone who could listen to me that risk is not in a linear. And they say why? I say you'd know about it if it were in linear. Because look here at the bottom. If you have a large linear exposure, it would scare the devils out of you. You see? But so you have to have a risk has to be something you don't see in a regular variation and has to harm you when there's large deviation. So this difference, look at the difference between the linear and nonlinear for large deviation. So I said you have to concentrate on. I had a little run-in with a company in this town called Fannie Mae. You heard that? All right. Where I pronounced that they were going to the cemetery. But I said it, not now, I said it before they went to the cemetery, but everybody thought I was an idiot, all right, for saying that. How did I detect it? A defector went to the New York Times with a risk report of these guys. Okay. And the New York Times came to see me, gave me the risk data. I fainted. The risks were very nonlinear. In other words, say interest rates or credit spreads or anything moves up 50 basis points, say they lose 10 billion. Another 50 basis points, they lose an extra 50 billion. An extra 50 basis points, they lose 500 billion. You get the idea. That kind of exposure accelerating, but massively accelerating. So when I saw that, then I knew I had a home run, okay? So, of course, I said it in the Black Swan. They're sitting on dynamite. I said it in the New York Times, and then there was some smear campaign against me, not naturally, you can see it, but it's fun. So this slide sort of explained my whole idea of nonlinearity. But now we can get more technical and see how we can take this to a lot of things, including your business, because you have the opposite reaction. But with this, let's stay at this slide, I can figure out why the small is beautiful. Think about why small is beautiful, because as you scale up, you have nonlinearity, the scale, and execution cost. And effectively, to execute in the markets, when you're very large, it costs you a lot more than very small. There's something, it's actually the cost increase at square root, cost of transaction, but they accelerate a very large transaction, which is why having small banks executing don't get as harmed as large firms. And this is an intuition I had when I saw LTCM blow up. LTCM was a fund managed by about all the creme de la creme of economists, including two who had the pseudo Nobel of economics, Byron Scholes and the other guy. And of course, they had no clue about anything. And then they had position and didn't understand that to unwind their position, you had an increasing cost per unit. But then I thought about it to say, okay, this can explain why firms don't survive. Because as you get big, you have economies of scale from pooling resources, reducing the numbers of water fountains per square inch, whatever it is, all right? But then at the same time, you're much more vulnerable to large deviation, and effectively that's what almost near bankrupted Société Générale when they had, because it cost a lot more to liquidate. Société Générale, a French bank, had a rogue trader with $50 billion in the drawer. It cost them 10% to liquidate it. It was a lot, even as steep. So this gives us an idea, for example, why projects. A friend of mine, I have no friend, no, okay, he's a friend of mine. He's writing a paper. We discovered that this curve applies to project size. This explains, this concavity, why projects typically cost more when they're large. Okay? And this curve is getting more concave when you have technology in it. The more technological components you put, it becomes even more people don't have inventories. You want a little more, okay, then the whole system gets jammed. This explains, for example, why by all costs, by all means, never goes through Heathrow. Last Friday, I was going from Zurich. I made the mistake, I was coming from Zurich, all right? And I made a mistake of going via Heathrow, all right? And of course, they had tenths of an inch of snow in Heathrow, all right? And they panicked more than you guys in London when you have snow, all right? But the point is that, you know what happened in Heathrow? They're so optimized that this tells you, for example, how optimized you are. It tells you the backlog. I have here a list of, what's this? No, I don't see it here. It tells you how optimized Heathrow is. There's a little bit of disruption. For example, you know if a town has too much traffic. As you increase the number of cars, the travel time has these delays. But of course, at the end, these curves aren't concave like this. Then they flatten out, all right? But the point is, in the concave part, you are short volatility. You are harmed by volatility. So let me continue. This is, for example, what I call pseudo-empiricism in finance. They have explosive packages. Up to 10 standard deviations is a word we're going to use, but we know it doesn't exist, all right? But assuming, that, it's sort of like we call a pseudo-standard deviation. Assuming the data were Gaussian, that would be a way to scale deviation. Up till 10 sigma, you have nothing from some option packages. Beyond, look at the losses. If you have a 20 standard deviation out of the money option, and an event happens of 23 standard deviation, you lose 400,000 times your premium. Okay? 400,000 to 1. That sort of. But typically, the variations are close to zero. So people tell you, these are expensive to own because, they don't happen to blow up, of course. But all you need is one event to happen like that every several 100,000 years, right, for you to collect. So visibly, small probabilities can have some attributes. Anyway, so the general rule is convex is good, concave is bad, and that's the way to verify, right? In reaction to random events. So sort of like I'm bridging. I started with some statistics because in honor of statistics, and then moved into my book that goes beyond statistics. Because as you can see, I can't measure rare events, but that stupid concavity thing, I can measure, or I can detect, or I can rank things based on. And we're going to see there are some heuristics we can use. That even if you have a bad model to measure payoff, you can still measure acceleration of harm, and that's good enough to take you a lot of places. So what it took me 25 years is to do this following step. From convexity, thickens right tail, likes volatility, and concavity, thickens left tail, dislikes volatility. You tell me you can pick it up in 20 minutes, formalize it in 20 minutes, pick it up in 1 minute. It took me 25 years. I'm a little slow, but that's okay. It's good enough, all right? So long as you get it, with this, you can go very far. Concavity, you detect concavity. So the beauty of it is I don't have to know the probability distribution of something. I can infer the probability distribution. And this is very interesting in measuring medical iatrogenics. I can infer the probability distribution from checking local convexity, and we're going to see how. I can infer the sensitivity or the thickening of probability distribution based on this, and back and forth. That's the interesting thing. Change of scale. If I can have access to the probability distribution, see how sensitive the distribution is, the tail below k, to the changing the scale, which could be standard deviation or anything. Or if I don't have that luxury, check local sensitivity to things. And we're going to see some example. Like we saw the example with a stone, all right? So this is sort of like, please ask me questions now because now I'm starting to see confusion, which I like, sort of, but, please raise your hand if there's a... Okay. So convexity effect. Now let's link this to things that people know, typically. Convexity effect is in English, and then we translate it into French. Don't cross the river that's on average X feet deep, because when you're talking about convexity, the average doesn't count anymore, all right? And this is well known. And of course, in French, it's a convex function of an average. It's not the average of a convex function, all right? And then we can figure out, and this is Jensen's inequality, very simple. But we can do something smart with it. I don't know if I can be technical. Please raise your hand. If one person raises his or her hand in reaction to the math, I'll move into English, all right? So, okay? Or in French, if you want. So French back to English from French. But so what I'm doing here, the biggest error in model, I teach model error, all right? I specialize in model error. And I tell them model error can come from 3 sources. The first one is your model doesn't have a significant variable. I've never seen it. I saw it once in my life, okay? Option pricing doesn't have the credit of the issuer, the riskiness of the issuer. That's one, okay? In any economic model. Typically, people over-optimize by dumping too many things in their model, okay? So that's the second one. The second error, actually the main error, is you do the following thing. You're working with the distribution of x, okay, with f the probability distribution of x, using parameter alpha. And alpha is a parameter that's uncertain. So what you do is you average alpha from the data and plug it into your equation to get f of alpha, all right? The difference between the error is that difference. I call it Jensen gap. I call it omega A, which is standard Jensen gap. And then I can look for the lower tail for the Jensen gap, which is the difference between integrating from the inside of the... I'm going to give you the example now in English, all right? So let's take a very simple example. Any one of you have had a grandmother? No? You have a grandmother, okay. You take a grandmother, and you're told that the grandmother has spent the last 2 days in some place. All right, say, okay, what was the average temperature there? You ask. You're told 70 degrees. Excellent, grandmother. And someone, no, you idiot. You didn't ask me what was the volatility of the temperature. All right. Because if you're fragile, you need acceleration. You depend on second order effect, which is acceleration. All right. So the second question is, what was the variation? Well, the first day temperature was, and she was outside, 0 degrees. The second day, 140 degrees, for an average of 70 degrees. So you know that the linear, so what we have here is H is health of a grandmother of T1 plus T2 divided by 2 is different from H, her health at 0 degrees, plus her health at 140 degrees, both of them dead, divided by 2, okay? That difference, we call the Jensen gap. Actually, I call it omega A. It's the difference, a misunderestimation by the model, of a variable deemed concave, all right? And this is the difference between a grandmother alive at actually optimal temperature and completely dead, all right? Okay, so that's the difference between these two. This is what I meant by the other equation, all right? And of course, Jensen's inequality is when a linear combination, okay, is higher. Like for example, health at 0 degrees, my health, okay, because this is why we're going to a restaurant, I wanted to go without my coat. And then, given that I have Russian hat, to just impress people, I put the Russian hat and I use the coat. But I wanted to have variations, thermal variation. Why? But that's antifragility. We're optimized for variations, all right? So up to some range. So spending some time at 60 degrees and sometimes at 80 degrees is a lot better than spending all the time. If I have that function, I'm a little convex, okay, then I like variations. So you can walk outside at 20 degrees a little bit and spend time inside at, it's a lot better than spending 100% of the time at 67.8 degrees, okay? That's Jensen's inequality. And with this, we can try to see why on earth in medicine, they never talk about Jensen's inequality, except in one case, lung ventilators, when it's so prevalent in biological domains. And we can do so much with it, okay, in figuring out that Jensen gap. So the nonlinearities and optimization, of course, we say cars in cities, if traffic, how convex traffic is. Incidentally, if you have an exposure to it that's negative, you're concave. So that's sort of like what I'm working on. Comes your business, I inserted this slide in a rush. So let's talk now about positive convexity, all right? For some reason, your business has positive convexity. Business means funding, research. You have small errors, and you have big gains. You agree? All right, so they have positive convexity. I measured something, the difference between knowledge and convexity. The biggest myth you can hear about, the biggest myth, is when people tell you, all right, that the business benefited from luck. That luck was a fuel for discoveries of Viagra, of this, of that, all these medicines. All right, penicillin, chemotherapy, from mustard gas, all this. No, nonsense. It is not luck. You have to have a convex exposure to a random variable. Convex exposure in terms of, let me find the graph of convex exposure to a random variable. You have to have more upside than downside from it should an event happen. Let me find the graph of the convex exposure. I don't have it, but it's okay. Okay, you know what it is. If you make more, then you lose. Then you are convex, okay? And it's supposed to be a good thing. You have more upside than downside. So in this book, I talk about the big error of conflation, all right, of thinking that a narrative and research got us to where we are. In fact, it's convexity. You cannot, and the evidence is right there. I mean, I give, first of all, I don't find counter-evidence. And then the other one, you can show mathematically that optionality means when you have the option, you have more upside than downside, like financial option. You pay pennies, you can make dollars. When you have optionality, then you benefit from randomness, you benefit from uncertainty. You can effectively measure how much in a random environment can come to you from optionality as compared to the predicting the events. You see, and you can do that. This is a Monte Carlo simulation, but let me show you something a little more analytical. Here I have there's something mechanism called convex transformation. Events can be symmetric as random variables. My function f of x, this is distribution of x on the left. F of x is convex. The distribution of f of x, my distribution, is to the right. This is the distribution that you have in your research portfolio, okay? Most of the time you don't do anything, you lose, or you waste your time, but you get good lunch, I think, no? All right? And once in a while you have a big bingo, you agree? But you don't have like a nasty, horrible loss on your hands, something, all right? You give someone $10,000, all right? That's all you can lose, you agree? You can't lose. This is exactly an option. So it's a $10,000, exactly an option. So we can exactly this is exactly how I map this, incidentally, where you pay a certain amount, all right, and your K is a strike. That's your K, and then you have the upside, and all you lose is that amount. Okay, that's your distribution. So here there is the symmetric distribution. If I have a convex transformation, then necessarily we have this result by theorem. I call it the barbell theorem. Don't ask me why barbell is complicated. It's fun in the book, but not here. But there's an attribute to all distributions that are right-skewed. You know what? They love uncertainty. Your expected return increases with uncertainty. Okay, this is what's central. If your distribution, any distribution, take a log normal, okay, say f of x, this is a Gaussian, f of x is the exponential. I'm exponentiating a Gaussian, and that was a log normal, all right? The log normal is right skewed. The mean of the log normal has 1/2 of sigma square in it. So when you increase sigma, you increase the mean by 1/2 of sigma square. You agree? Okay, so all distributions that are right skewed, it's worse when you have power law tails, so the Pareto distribution visibly, okay? And every time the scale of the distribution is present in a mean. You increase the scale, you also increase to the point where it's hardly possible to distinguish for Cauchy between a mean and a scale. You see? Well, there's no mean anyway, right? And there's no scale, right? So you get the idea. So now let me work again with fragility. I think in terms of fragility and antifragility, like one of an option trader, and the same things. One has negative sign. Let me take your business in reverse. I came from London. I came from Zurich to New York in order to, and I had another talk, but you see, I worked hard to come here. So My plane was supposed to be are supposed to take maybe 9 hours. All right. It took me only 19 hours. All right, to get here. So you inject uncertainty in the system, you increase travel time. You could probably decrease travel time by 5 minutes. But have you ever seen someone on a 9-hour journey get there 8 hours early? No. 8 hours late happens to me so routinely it's not even funny, all right? Okay, tonight is going to happen to me again going back home from here, all right? I'm going to be maybe, it's okay, I have a book to read, and I have a phone, a lot of things. Okay, but don't worry. So you understand? So if I take a distribution that's skewed left, and skewed left means it's a cost for me. The tail is a cost for me. I inject uncertainty in it. What happens? It degrades. You agree? Well, that's because you're concave. When you're concave, you have that attribute. If you guys are convex, I inject uncertainty, it increases. It's exactly like an option. An option is a convex transformation of the underlying. The underlying is x, and option is f of x. I have the right max s, minus k0, all right? The payoff at the end minus k. So the payoff from the option is convex, all right? So you see, you want maximum uncertainty. People don't think in these terms that you want maximum uncertainty, all right? But you want maximum uncertainty, but you got to play it right. What do you do when you have the option on your hands? Aha. Now, this is the only thing I can say with confidence because that was my business for a long time. Okay? So let me come back to the book and tell you the big conflation, all right, of Aristotle talking about Thales. The first option on record was in Thales of Miletus, who was a Phoenician, and like all Phoenician, had pressure from his grandmother, like mine, to get rich, right? That's the idea. You have to, okay? And so, but he wants to be a philosopher and wants to also show his buddies and family members that being a philosopher was something he does by choice, not because he's too stupid to get rich like his cousins. You get the idea? All right. So how did he solve the problem? One day, as Aristotle reported, he went and put a down payment on every olive press in the area. Small payments. And he had, as a counsel, he had nothing to lose more than that down payment. In case, okay. And what happened is that there was a huge crop and huge demand for olive presses. So he went back and sold these rights, okay, let people out for a huge profit, and then went back to philosophize. Okay, very simple story. Beautiful story in many respects. The interesting one is that Aristotle, while describing it, said thanks to his knowledge of the stars, okay, he predicted the thing. He didn't get the point that it's not his knowledge of the stars. The guy had a f of x, all right, that was convex. So there we go. Here we have two stories, and that's most of the book. It irritates a lot of people. It's highly anti-intellectual by showing you that convexity trumps knowledge any time of the day, provided you know how to use it. You have to exert your rationality by ratcheting, you see. So here we have these two things. Mathematically, knowledge you can't map mathematically easily, you see. So we're going to make rules, and I'm sure in the conversation comes of how you fund things, all right? You fund things on convexity, particularly if it's open-ended, rather than on what you think you understand, because what you think you understand is heavily marred with psychological narratives. And I call it the narrative fallacy in a black swan, okay? So this is the idea, and this pretty much is what happened in a lot of the big heydays we had of pharmacological discoveries, where they had no clue about the underlying. No, I don't know. You're not supposed to curse in a governmental thing, no, because it's going to be on the web. Please edit it. But they had. Sorry.
You're not asking for funding.
Yes, that's okay. Yeah, that's the idea of being independent, all right? And you can get a hint with the Thales story, all right? But the idea is the understanding. The tension between understanding, all right, and doing when they had no clue and knew they had no clue. They were trying out dyes, doing tinkering, trial and error. Now, trial and error is a misnomer. It's not trial and error. It's trial with small error. You're convex. Small, you're convex. Small loss. Okay. To repeat for those who want convex, it's very simple. If for the same movement down, you lose less than you make. If a movement up, you're convex. Or if something moves up 10%, you make, say, $1. And after 10%, you make $2 more, then you're convex. Convex means acceleration of gains. It doesn't have to be smooth, but so that's the idea. Now, as an option trader, we always realized that I had no idea what's going on. The only idea is if you buy a lot of options cheap, I couldn't care less what's happened, all right? So that's the idea. That you care about the convexities of the option portfolio. So, and then the payoffs, but remember, I started by saying the process has fat tails. Research payoff has fat tails. This is the payoff. You try, look at this, and this is boom. This is pretty much what you get. You know what? I'm underestimating. This can be much taller, and these smaller to scale up. It's shocking if you do it right, how if you take the history, this is, when you have something like this, what do you want to do? You cannot afford to miss that big stick. Hence the 1/n rule. Okay? 1/n rule tells you the following. Let me give you a very simple example of how I understood someone who knew it heuristically but not mathematically. When I went to Random House, I was not a best-selling author, so they make me wait in the lobby, which is what they do to all authors who are not on the bestseller list. You make it on New York Times bestseller list, and automatically you have different treatment. Okay, an assistant comes down and stuff like that. And all right, so they may even have special elevator for them. But at the time, I was waiting in the lobby, and they make you wait. All right, to tell you that you have to write whatever it is. So I looked in the lobby of Random House. Boy, there are 57 publishers in the building. Different names. I was wondering what was going on. Then I figured out that they all belong to Bertelsmann. They own Random House, and they own about every book that prints they want to own. Why? That's what they're playing. Because unless they're very large, now they have 25, by now they have 25% of the market of books in the U.S. They can't get that. All right, so that's the mode. Boom, small, 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 small. All right, it's called 1/n rule. And effectively, if you follow models that use Gaussian distribution, you end up with a small allocation. And effectively, this shows you pretty much what I said at the beginning of 12,000 listed companies, and I don't know how many that joined the market, how much of the capitalization belongs to the super minority of a few hundred companies. All right, so you have an idea that one company in 500 is going to represent most of the bulk of the return. One investment in the long run, okay? Okay, so this is pretty much how it can work. This is the second rule is 1/n. The third one, there's something called the cliquet property. The cliquet once you know that you're dealing with an option, which is what you guys are doing, are you guys dealing with an option? Yes, no. Yes? Then there's a cliquet property. A cliquet property tells you the following. There's something called a resetting option. I can buy a 5-year option, stick it in a drawer, come back 5 years, see what happened. Or I can buy a series of 1-year option, resetting every year, ratcheting up at whatever value they have. And then I start new. Okay, it's called the cliquet property. I call it the cliquet property. The series of 1-year option is worth vastly more, a lot more than one 5-year option. Okay, so in other words, you make your policy. Don't give long-term investment. Give a lot of small-term, and then tell the guy to come back every 6 months for a conversation. All right, what did you do instead of giving them the money? So redecide whether you want to fund them or not every 6 months. That's sort of like, they won't like it, so what, all right? But sorry? They don't like it, that's it. So but that's life, all right? You make them come back, and you can see them. If they're pleasant to have coffee with, it's good enough, all right? So they tell you, oh, we're going to go for a long run. The problem is someone's going to come here obsessed with an idea that's going to take them somewhere, all right? Tell them, very nice. This is 1/n, small amount, and then you. So this is what I call the non-narrative property. is don't fell sucker for a narrative, because narratives is something, we invent. Optionality is exact non-narrative, anti-narrative. It's a little complicated because I had to run in with a lot of people who give narratives of why we do things. Who cares about narrative? We don't function as narrative. We function with optionality. So it has some philosophical implications, anyway. And I call it non-teleological property. Think about a highway. You don't want to be on a highway going without exits because you want to be able to change your mind. Optionality allows you to change your mind. That's the optionality. You have a right but not an obligation. So the researcher himself should be able to follow his optionality, right? There's two, and then the book, people don't like it because I have a character called Fat Tony who argues with Socrates, and they're fighting between heuristic knowledge and top-down knowledge, all right? And they say the problem, my whole problem in life is that I think that you don't have to understand things to function properly, and the more you understand things, the more you're a sucker. You think you understand it. And Nietzsche, so Nietzsche, but I'm not going to say it as an option trader. I use proxies. So Nietzsche said the problem of Socrates is that he thinks that everything that's not understandable, okay, the unintelligible, okay, is not intelligent. And that's a big problem, all right? With optionality, you don't have to, worry about the unintelligible, all right? As a matter of fact, the unintelligible had more potential. More variance. See? So that's the idea. And of course, Fat Tony is a guy from Brooklyn who definitely understands optionality. He got rich as an option trader. Fat Tony, very fat. They're characters. Nero Tulip, classicist, Fat Tony who never read a book and wanted to write one. And Socrates and stuff like that. So Fat Tony starts arguing with Socrates, all right? And I'll let you know who won the debate, all right? Book 4 over here. So, and then of course we have premium for simplicity was a very simple thing. When someone's giving you a story, there's no premium for simplicity. Okay, but in reality, there's no penalty for simplicity. In academia, there's a penalty for simplicity. Okay, so and then finally, the only way you can be rational with options, you have to be very, very rational with options, not to be able to use them properly. And understanding that the non-discovery is a huge asset, okay? So by cataloging negative discoveries, okay? So you don't waste your time twice, all right? Looking for your wallet in the same spot, all right? And that's the problem of negative, you need a catalog of negative stuff to optimize on your option because you've paid already to explore that territory. So that's what so you have to be very rigorous with options because most times, say in pharma, they're looking for this, not for that. They discover something else. And no, that's not what they're looking for, you see. Optionality is when you don't really care about it. You just change. So the teleology is you know exactly where you're going. You have a goal. Now, of course, that business plans are pure bullshit. They don't work, all right? I mean, you can probably make them work by making them, it's good for therapy, business plans. But, of course, we know they don't work, okay? We have evidence they don't work. We have even evidence that those who don't have business plans do better than those with business plans. Okay, so there are ways. Okay, so ways to fund research. You want to maximize side effects. That's optionality. Maximize being able to harvest optionality. We can do a lot of things with this. But all I'm doing here is introducing the notion of convexity into the dialogue, and I continue with this. One thing about big data, we're talking about convexity. I just added the slide to show you. This is the number of variables. As the number of variables increases, here, the number of spurious correlations increases nonlinearly. Okay? So you have a researcher. He doesn't even have to be a fraud. A lot of economists I know don't know there's a frauds. They just mine till they find something and then invent a story and give you a P. This is why it doesn't work. But they don't have to be a fraud. It's just a matter. That's the point. This is what observational studies don't replicate. And this is the same thing. I'm going to skip all my stories about meta-probability because meta-probability, I proved one thing, is that fat tails, actually I didn't prove this, but I proved something more complicated. The fat tails come from unstable variance from that equation that I showed, the Johnson inequality earlier, omega alpha. The difference between like a grandmother temperature, all right? And okay, same story here. And then with this, I can do something complicated. I'm not going to show it to you now, not to thing. We're getting to the close of my thing, and then Q&A. Before I finish the Q&A, I'm going. Okay, let's go to medicine. All right, very simple. Same map. Medicine. This is a probability in payoff space. Okay, and this is why I'm very angry with medicine, because we spent so much money and wonder what to do with probability distributions of harm. Okay, anytime you take something that doesn't have benefit in medicine, you have this big, thick left tail. Not only I can show it in probability space just by argument, but I can prove it mathematically from convexity in response to an item. And let me do both, all right? You know that nature has been around for, I'm told, 3 billion years, maybe more. Okay, science this week has something new? All right, okay. So you know that there's nothing you can put in your system that will make you unconditionally better. You agree? So concave is when you have small upside, a lot of downside. Okay, so you have iatrogenics, we call it iatrogenics, which is harm that you get from medicine. It turned out that someone told me I was wrong and gave me aspirin as an exception. But that argument went bust yesterday. Aspirin triples your chance of blindness or whatever. Okay, it turned out. There's nothing, because nature optimized it, okay? That's for no deviation, you're not ill at all. But now let's say you're slightly ill or very ill. The distribution changes. No, if you're, this is, what is this? Okay, these drug benefits, okay. If you are slightly hypertensive and you take a hypertension medicine, what is your chance of benefiting from a drug? Order of magnitude, sorry? How much?
Small.
How small? Number needed to treat. How many people you give them a drug for one person to benefit? Somewhere between 60 and 70. All right? And they prescribe it to people. So, okay, slightly hypertensive. This is what you see. You have small benefit from it, 1 in 67 chance, and you don't know all the harm you can get from it. Could be epistemic, you don't know the harm, or it could be effective, because we may have a right probability distribution. Now let me continue. You're very hypertensive. Okay, something like systolic is 185, 190. You take a drug, what's your chance of benefiting from it? Goes up to 80%. Okay. So now let's think about it. Then your distribution is convex. All right? My distribution is convex. I want to take 3 times, 4 times the medicine, see 5 doctors, take maybe 5 medicine, whatever it is. You should be over-treated when you're very ill. Okay? And not treated when you're mildly ill. But let's think about it in terms. Yeah, one sec, let me give you the stat and then take your question. Think about it in terms of distribution. How many more? What's the ratio of people who are mildly hypertensive to highly hypertensive? 1 sigma, say, to 4 sigma, or whatever it is. 1 sigma to whatever sigma they call hypertensive. Between 4 and 5 sigma, something like 5,000 times. You have 5,000 times more people who are slightly hypertensive with an NNT of 1 in 67. So if you're pharma, where would you go? Find people mildly ill, get them on your drug, and they won't die because they're only mildly ill, so you keep them for a long time. The book has complication. I talk about via negativa, removal. When I add, anything I add to you has a multiplicative branching side effect, whether I add to you or a system or intervention. But if I remove smoking, incidentally, I cite something that shows that, and the data seems okay, that you save more lives than anything done since penicillin by banning smoking. Diabetes. Now I hear people want $1 trillion, but $1 billion, whatever, for resveratrol, shmevesveratrol, this, okay? Take someone to Siberia. I'll give you the address. 6 weeks, they put you 6 weeks at 500 calories a day. They bring you back with a better, right, and no side effect, better, much better results than if you were on shmevestatol, trevestatol, this other medicines, all right? All the via positiva medicine, and definitely known side effects, all right? If you remove smoking from someone, you know that now, okay, so this is sort of like the idea of via negativa. So to make things convex to concave and stuff like that, I have 570 pages on this and an extra 500 pages of math on the web for those who have insomnia to explain these things. So this is sort of like my idea. The final thing about variation is there's something interesting. Let me go back to Jensen's inequality. That'll be my last slide. This is my last slide. No. If we know how to work with convexity, then you realize that there are a lot of results in medicine that don't seem to map these things probabilistically or formally. But fasting, intermittent fasting, Jensen's inequality. If I give you less calories today, more tomorrow, supposedly someone comes up with a theory, SIRT1, SMIRT1, all this, okay, but the idea is that you have the same long volatility. You benefit from variation. If you benefit from variation because you're convex, in the convex zone. Of course, natural phenomena are convex and then concave, but we're still in the convex phase. So this is sort of like the idea and all that comes down to the same equation in the end. Research, fragility, antifragility. What I call antifragile is what likes variability. If your body likes thermal variability, likes caloric variability, consumption, energy variability, stuff like that, if you lift weight visibly, you do a lot better lifting 50 pounds once than lifting half a pound 100 times, all right? So if you build more muscle that way, then visibly you have a convexity, all right? Now, I was wondering why all these were not put together on the same roof. We only found one citation using one class of lung ventilators where they give people 50% of the dose, randomize the dose. We're getting on average some 80% to 120% sort of, alternating is a lot better than giving 100% of the thing. So they found it in one domain, but there are like 500 domains where it can be applied. And all fall from the same convexity thing. So thanks for listening to me, and hopefully the Q&A will last. Thanks.